So hello everyone, my name is James Konoske. I'm from Point Loma Nazarene University in San Diego, California. And I joined Dr. Scott Linder this summer to work on inference for correlation when data are subjected to type 2 censoring. Before jumping into our project, I want to go over a few terms. The first being correlation. Correlation is used to test linear relationships between quantitative data. Correlation is denoted by lowercase r, and is defined on the interval from -1 to 1. With values of correlation closer to the boundaries of 1 and -1, considered to represent high or strong correlation. And values of correlation closer to 0 are considered to have low or at times no correlation whatsoever. An example of data that we suspect to have high correlation would be something like your caloric intake versus your actual weight. An example of data that might have low correlation or at times no correlation at all would be how much coffee you drink and the price of your calculus textbook. The next term I want to go over is type 2 censoring. Type 2 censoring occurs if an experiment has a set number of objects, subjects, or items, and the experiment stops when a predetermined number are observed to have failed. To give you a better understanding of what type 2 censoring is, let's pretend I am a head researcher at General Electric, and my specialty is within testing light bulbs. And right now I want to test the correlation between X and Y, X being the light bulb's longevity, and Y being the amount of watts that the light bulb uses. So there's two ways that I can test this theory, or test the correlation. The first method would be to wait for take 10 light bulbs and wait for all 10 light bulbs to burn out. In this case, and our sample size is equal to 10, and P, which represents when the experiment ends, which is equal to 10. And our other way, that's an uncensored experiment. Our other method would be to use a type 2 censored experiment where we take 100 light bulbs and we wait for the first 10 to burn out. In this situation, N is equal to 100, and P, our experiment, ends at 10 light bulbs. Either way, both experiments give you 10 burnt out light bulbs for you to analyze, except method A, you are waiting for 10 random light bulbs to burn out, so that could take a very long time. Whereas in method B, we are waiting for the 10 weakest light bulbs to burn out. And we suspect that that is going to affect the sampling distribution of correlation. To demonstrate this, we simulate a whole bunch of different sampling distributions of correlation with different values of NP and rho, or NP. And the sampling distribution is displayed. N is equal to 50, meaning the sample size is equal to 50, or we have 50 light bulbs to begin with. And the different experiments ended at different values of P. So in this case, P is equal to 4, so we ended the experiment after 4 light bulbs burnt out. As you can see, as the effects of censoring decrease, we start from a flat distribution to a trend at 0.1, which is expected because in our simulation, rho is equal to 0.1. As the effects of censoring decrease, we get higher frequency bars and less variance between the distribution. So now that we've displayed that since type 2 censoring affects the distribution of correlation, we began just looking into how could we approximate the sampling distribution of the absolute value of R. You may be wondering to yourself, why the absolute value of R? Well, we suspect that we are able to do this according to the beta distribution. The beta distribution is a family of continuous probability distributions defined on the interval from 0 to 1, parameterized by two positive parameters denoted by alpha and beta. The reason we suspect that we could approximate the sampling distribution of absolute value of R by the beta distribution is because not only are both defined on the interval from 0 to 1, but as you can see in these graphs, the beta distribution is very flexible. As you can see from the black line, we have a flat distribution as we saw before. We have skew we have uniformity, along with many other different shapes that the beta distribution is able to display. So to begin actually looking into whether the beta distribution actually could approximate the sampling distribution of absolute value of R, we simulated 1,000 absolute values of R's, where we fixed the values of NP and rho. We then took the same sampling distribution and fit a beta distribution onto it. In this situation, alpha was equal to 3.12 and beta was equal to 1.45. You may be wondering, how did we get those parameters? In order to do that, we use the beta distributions method of moment equations, which simply are able to predict alpha and beta that correspond to different values of fixed NP in rows. So what we did was we took NP in row, and we created like 1,000 different values of absolute value of correlation. We took the means of those and we took the sample variance of those and then plugged them into the MOM equations, where the mean is represented by x bar and the sample variance is represented by s squared. We do this repeatedly for many different combinations of NP in row, and then at this point we have a very big library of values of NP in row that correspond to alpha and betas. As you can see, as p becomes closer to n, or the effects of censoring becomes less and less, alpha and beta tend to grow in size. And just from this trend, we think to ourselves, is there some type of formula that can represent this trend where NP in row can be plugged into and created alpha and beta values? So in order to do that, we begin our regression model testing, where you can plug in an NP in row and hope to get an alpha and beta that represent a beta distribution that approximates the sampling distribution of absolute value of R. So once we've created these different regression models, we're ready to begin our hypothesis testing, where our null hypothesis is that if you take that the sampling distribution of the absolute value of R can be approximated by the beta distribution, where alpha and beta, the parameters of the beta distribution, are created by these two beautiful formulas that were created by regression modeling. So if our null hypothesis is true, if we fix our values of NP in row, the sampling distribution of absolute value of R should be represented by a beta distribution that was created by our regression models. So what we did was we took the beta distribution, we then broke it up into 10 different bins that are supposed to represent 10% of the beta distributions And so then we simulated 1,000 new absolute values of R's with the idea that 10% of those absolute values of R will land within each bin. So in this case, because we started with 1,000 new absolute values of R's, we hope to see approximately 100 absolute values of R to land within each bin. Once we've done that, we're able to begin our chi-square goodness of fit testing, where our observed is equal to whatever value is within a bin, and our expected equal to 100. With the chi-square goodness of fit testing, we're hoping to get chi-square values that are closer to 0, which means that our sampling distribution is closely approximated to our beta distribution. And we hope to get p-values that are not close to 0 whatsoever. Before, I had terrible p-values that were all very, very close. Not that these are perfect, but as you can see, in certain situations our chi-square value is closer to 0, where in other situations they're not. Our p-values are really sporadic, and so moving forward, I want to look into fine-tuning the regression models that we use to create our alpha and beta distributions. And then also, we use the method of moment equations to predict alpha and beta. There's also the maximum likelihood estimators that could also predict alpha and beta and are considered to be a little more precise. But due to time constraints, we weren't able to actually use those equations. Another thing you could do is that we didn't do as much was take the alpha and betas and get like a bigger average of like, so you would do the MOM equations multiple times and get an average of what those values would be. And then after that, once we've determined that the beta distribution provides an adequate approximation of the sampling distribution, we could invert it and construct confidence intervals and be able to predict rho, which is normally an unknown value in the real world. And that concludes my talk.
James, questions?
Questions? Yes.
So if you're finding about your variables, remember, and your full sample size B is sort of your subsample size, what is rho?
So rho in the real world is usually an unknown estimator. And so,
Of what? What does it represent?
Could you help me with this?
So when you say,
Population
okay, so that's the
correlation.
issue, got it. So when you ran your sample, you had a population correlation of point one, point
Yeah, for these graphs, and then we did different values of rows, so rows equal to 0.1, 0.3, 0.5, 0.7, 0.9. And so beginning our regression model, so before I presented this, I had a model that represented every single combination of NP and rho from 0.1 to all the way to 0.9. So in order to make it better, I compartmentalized it and made different regression models of different values of rho, and that seems to have helped, and I'm suspecting if we do more work on that.
So your overall question is something like, if you had a good idea of what kind of correlation you wanted, how much of the sample do you actually have to sample before you could correctly estimate this? Am I getting at, so your idea, like if you had some idea that the correlation you were looking for was this number, and you had a sample size of something, you'd like to know how far into the sample you have to go before you get a good estimate?
Yeah, so two different questions you could ask. One question is to achieve desired power or precision in estimating rho, how large the sample will be, what experimental conditions are ideal, right? So that's one question further down the road. At this stage of the game, he constructed regression models that depend on rho, which we don't know, right? So what's going to have to happen is he's going to have to build regression models through which you can substitute some kind of alternative for rho, perhaps the sample correlation itself, which has an awful lot of variation and creates its own set of problems. Or build a model that doesn't depend on that.
So it seems like you got data. Was that coming from simulation or?
All this was simulation.
Yeah. How were you simulating that?
So we created different absolute values of correlation using so fixed NP and rows. So, or I believe we used sigma. What were the values that we used?
So you fix the population characteristics.
Right.
You can standardize things, so you can just arbitrarily say population means are 0.
Right.
Population standard deviations are 1. Because everything can be scaled accordingly. Right? And you just generate bivariate normal random variates. Generate the sample correlation from the censored sample. Repeat.
Right. Any other questions?
All right, let's thank